A wind tower is a traditional Persian architectural element to create natural ventilation in buildings. Windcatchers come in various designs: unidirectional, bi-directional, and multi-directional. Windcatchers remain present in many countries and can be found in traditional Persian-influenced architecture throughout the Middle East, including in the small Arab states of the Persian Gulf, Pakistan, and Afghanistan. Background: Central Iran shows large diurnal temperature variation with an arid climate. Most buildings are constructed from thick ceramic with high insulation values. Towns centered on desert oases tend to be packed very closely together with high walls and ceilings, maximizing shade at ground level. The heat of direct sunlight is minimized with small windows that face away from the sun. The windcatcher's effectiveness had led to its routine use as a refrigerating device in Persian architecture. Many traditional water reservoirs are built with windcatchers that are capable of storing water at near freezing temperatures during summer months. The evaporative cooling effect is strongest in the driest climates, such as on the Iranian plateau, leading to the ubiquitous use of windcatchers in drier areas such as Yazd, Kerman, Kashan, Surjan, and Bam. A small windcatcher is called the shish khan in traditional Persian architecture. Shish khans can still be seen on top of anbars in Kazvin and other northern cities in Iran. These seem to function more as ventilators than as the temperature regulators seen in the central deserts of Iran. Windcatchers in Egypt. The windcatchers are known in traditional Egyptian architecture in ancient Egypt as demonstrated in windcatchers on the pharaonic house of Nebamun, Egypt, 19th dynasty, c. 1300 BC, British Museum. It was revived in Neo-Islamic architecture as the works of Hassan Fadi. In Egypt, the windcatchers are known as malkaf. Structure and architecture. Windcatchers tend to have 1, 4, or 8 openings. In the city of Yazd, all windcatchers are 4 or 8-sided. The construction of a windcatcher depends on the direction of airflow at that specific location. If the wind tends to blow from only one side, it is built with only one downwind opening. This is the style most commonly seen in Mebod, 50 kilometers from Yazd. The windcatchers are short and have a single opening. To keep buildings free of dust and sand blown in from the desert, windcatchers were built facing away from the wind. Function. The windcatcher can function in 3 ways: directing airflow downward using direct wind entry, directing airflow upwards using a wind-assisted temperature gradient, or directing airflow upwards using a solar-assisted temperature gradient. Downward airflow due to direct wind entry. One of the most common uses of the windcatcher is to cool the inside of the dwelling. It is often used in combination with courtyards and domes as an overall ventilation and heat management strategy. It is essentially a tall, capped tower with one face open at the top. This open side faces the prevailing wind, thus catching it, and brings it down the tower into the heart of the building to maintain air flow, thus cooling the building interior. It does not necessarily cool the air itself, but rather relies on the rate of airflow to provide a cooling effect. Windcatchers have been employed in this manner for thousands of years, as detailed by contemporary Egyptian architect Hassan Fadi. Upward airflow due to temperature gradient, wind-assisted temperature gradient. Windcatchers are also used in combination with a qanat, or underground canal. In this method, the open side of the tower faces away from the direction of the prevailing wind. By keeping only this tower open, air is drawn upwards using the Coanda effect. The pressure differential on one side of the building causes air to be drawn down into the passage on the other side. The hot air is brought down into the qanat tunnel and is cooled by coming into contact with the cool earth and cold water running through the qanat. The cooled air is drawn up through the windcatcher, again by the Coanda effect. On the whole, the cool air flows through the building, decreasing the structure's overall temperature. The effect is magnified by the water vapor from the canat. Solar-produced temperature gradient. In a windless environment or waterless house, a windcatcher functions as a solar chimney. It creates a pressure gradient which allows hot air, which is less dense, to travel upwards and escape out the top. This is also compounded significantly by the diurnal cycle, trapping cool air below. The temperature in such an environment cannot drop below the nightly low temperature. When coupled with thick adobe that exhibits good resistance against heat transmission qualities, the windcatcher is able to chill low-level spaces in mosques and houses in the middle of the day to frigid temperatures, directing airflow upwards using wind-assisted or solar-produced temperature gradients has gained some ground in Western architecture, and there are several commercial products using the name Windcatcher. Modern applications. The windcatcher approach has recently been utilized in Western architecture, such as in the Visit Center at Zion National Park, Utah, where it functions without the addition of mechanical devices in order to regulate temperature. Using aluminum for the windcatcher provides a more efficient capturing system, allowing for wind capture from multiple directions. The Kensington Oval Cricket Ground in Barbados and the Saint-Étienne Metropole Zenith both use this method. Gallery.